Okay, y'all ready? We've been talking about delta H, guys. We've been talking about delta H, and I've shown you where it comes from with bond enthalpies. I've shown you another way to estimate it with standard reactions like Hess's law. And I have those quizzes up on D2L now. Now I'm finally showing you how you could actually measure this. So if you have this reaction, and you wanted to find out what is the delta H of this reaction, essentially what you do, you guys, you put it in some sort of insulating container, like a styrofoam cup, and you have it in here, in water, and as soon as you've got your, let's say you've got your HCl down in here in this water, this is aqueous HCl, just an acidic medium, and then you drop in the magnesium, and then you immediately put a top on it, and it's got a hole in it with a thermometer down in there. And basically, you measure the rise in the temperature, and then you can tell how much heat came out of the reaction. We're going to do something like that for lab next week. But looking at example 9.8, I've got a picture of it, so I'm going to go back to the camera. So let's say they put the experiment, they put 0.58 grams of magnesium down in there. The HCl is a little bit excess, just to be sure this is the limiting reactant. The temperature change, this is 100 milliliters of solution. And the temperature change is temperature initial, 25.6 degrees C. Temperature final in that cup is 32.8 degrees C. A couple of more facts that you need. It tells you the density of this solution is 1 gram per 1 milliliter. They also give you a heat capacity to deal with. We call it, I'll just say heat capacity of the solution. Joules per gram per degree C. And they're saying you use 4.18 joules per gram per degree C. That should be enough to solve. So we need joules, and you can find it like putting the mass times delta T times heat capacity of the solution. So what can we do? To find the mass, you're going to use the density. If you've got 100 grams to 1 milliliter, and you've got 1 gram, 1.00 grams per milliliter, and you've got that many milliliters, it essentially tells you that you've got 100 grams. Milliliters cancel. Grams of solution. So that's our mass. Times our delta T we get from here. Delta T equals final minus initial. $32.8 minus 25.6. So delta T equals 7.2. And what we're using for heat capacity is joules per gram. That'll tell you how many joules came out of the reaction. The way, we did a similar calculation of this before, but it would have looked like this to you. I would have gone 100 grams, delta T 72, and then 4.18 joules per gram. But essentially, we're just multiplying across. 100 times 7.2 times 4.8. Four significant figures, 2. I'm going to need 2 here. My calculator says this. Joules. Since I'm only keeping those 2, I kind of have to do this in scientific notation. 1, 2, 3. But we have to figure this out in grams per mole. So we're going to use this to find out the grams per mole. Grams of mg, 24 point something per mg. Of mg, mole of mg, and what we get for moles, 0.158 divided by 24. 3 significant figures. We're going to keep these, so we end up at 650. That's how many moles of Mg was put in. So our final step here is we're going to get grams joules per mole. 3.0 times 10 to the 3 joules to 0.00650 moles. Divided by 0.0065. This is 2 significant figures, so I'm only keeping this. So 460,000 joules per mole. But of course, you could also go 2 significant figures. I'm not indicating 2 significant figures here, and really the only way to do this is, again, scientific notation. So if that's correct, and I could also do it in kilojoules per mole, 4.6 times 10 to the 2 kilojoules. Either of those would be correct. Oh, I forgot the negative. Here's how you know it's negative. Because temperature went up. So heat came out and heated up the solution. Should have a negative there. So using calorimetry to find out the actual, this is how you measure the delta H for a reaction. There is another one under this practice thing. Practice. So we were given a density to work with, a heat capacity to work with, the temperatures to get a delta T, and these grams to work with. You guys okay with that?
Did this C stand for?
This heat capacity. Joules per gram per degree C. You guys okay with that? let me do another one that's very similar. This one, the reaction is GnO3 aqueous plus HCl aqueous gives us AgCl solid. Alright, so what if we wanted to find delta H for that reaction? This is just another example given in example 9.8.
Did you say a second ago that we would use a limiting reactant?
Yeah, it's described in the problem there. I just didn't read the whole problem. This one is slightly different where we have 50 milliliters of 0.100 molar HNO3 solution. 50.0 milliliters of 0.100 molar HCl solution, and we pour them together. So we'll be finding our moles this way. Get my densities and stuff. Okay. Temperature initial. Temperature final. 24 T1 degrees C. So again, heat came out. And again, we're told to use 1.00 grams per milliliter for the density. And I guess we're using the same heat capacity at 4.18 joules per gram per degree C. That's all the information given to us. What you need to know is the calculation to find the joules is capacity of the solution. So we'll do that first. Maybe I should find my delta T first. 24.21 minus 23.40. Minus 0.81 degrees C change. So this is 0.81. I guess I should say degrees C. Mass. Okay. We're going to use this again. So this just assumes it's 1 gram per milliliter. And 50 milliliters plus 50 milliliters. The problem describes this, that you pour them together in a calorimeter, that is the styrofoam cup. So we have 100 grams. 4.18 joules per gram per degree C. So we get for our joules 100 times 0.81 times 4.18. I've got that for joules, but really we're at 2 significant figures here, so I'm really keeping 340 joules. So it's 50 milliliters of this solution and 50 milliliters of this solution, which means 100 milliliters. And then we're assuming a density of 1 gram per milliliter. But those are given in the problem. You just have to figure out the total milliliters. Okay, we do that. These are all 1 to 1 to 1 to 1. So the grams per mole here is the same for all of them. But let's just find the moles of this. Whatever moles we find of this, that's exactly how many moles this will be. 50.0
milliliters, 1 liter, and then the 0.10 is 0.100 moles to 1 liter. Milliliters cancel, liters cancel, this is mole. So this will tell us how many moles of AgNO3 we have. 50 times 0.1 divided by 1,000. I've got 0.005. Exact. That's 3 significant figures. That's 3. So I need to put 2 zeros here. So the grams per mole, the joules per mole is 340 joules divided by 0.00500 moles. Joules per mole is 340 divided by 0.005. You could say 68 kilojoules per mole. You'll do 6.8 times 10 to the 1, 2, 3, 4. Joules per mole. You could also do 6.8 times 10 to the 1 kilojoules per mole. So, any of those work. Yeah, that one works too. Because if I don't put a decimal there, that means 2 significant figures. I don't think I gave the answer to that one, but hopefully I did it right. So calorimetry is how you actually find the delta H for reaction. I go through that too fast. The only other one of these I gave for you to practice. 71. It's definitely not the one I wanted. Oh, I'm in the gas hall. Okay. It's the wrong chapter. 71. So there you go. So stick with that example in 71 here for practice. You get the answer to 71 by looking at the very back of the book. But we will do a calorimetry type thing next week for lab. And really the only thing in this list, I keep saying I'm going to post this for you guys, so you have something to follow. Heat capacity and specific heat, there's the examples. Covered that already. Reaction energy, stoichiometry we covered. We've covered all of these except for this one. And the rest of today I'll do this stuff. I'm going to do this too. So I'm going to move to the next chapter, and I may or may not come back for the heat information. Those are the things we've covered on the left there so far for test. I have almost all those quizzes up. Calorimetry is the one missing. Okay, chapter 10. Pulled out table 10.1. the idea of pressure, I'm introducing something we really have to talk about. There's some examples to follow. But this is all about table 10.1. So I'll write down what's in this table, but I've also got it in PowerPoint, so I will give you that test. I'll write these down. Okay, I don't know why science holds on to a bajillion different ways to express pressure. I think mostly scientists use atmospheres for pressure. Here's some pressure, but there's a bunch of these. Something called the Pascal. And I'll write this, I'll tell you what this is in a minute. 3, 2, 5. Pascal, we use PA for that. There's PSI, you may have heard of that, that's pounds per square inch. 14.7 PSI. There's something called torr, but it's the same thing as 1 millimeter of mercury is defined as a torr. I'm not going to go into all of these, but like, you've heard of mercury, it's a metal, it's a liquid at room temperature. If you put it in a U-shaped tube and the levels are even, and then you seal this in and you apply some pressure, like just with the atmosphere or whatever, it will push it down a little bit, and this side will go up a little bit, and you could measure those milliliters, and it's a standard way to measure pressure. So millimeters of mercury is that apparatus I just described. It's also called a torr, but I won't go into that stuff. 29.92 torr, aka 1 millimeter of mercury. Okay, and people still use inches of mercury. So INHG is inches of mercury. Torr was 760. 9.92 inches of HG. Also something called the bar. And then visible atmosphere. That's essentially what's in table 10.1. I'll give you those on a test. Most of the calculations I have to do uses atmospheres. That may not be true, but let's look at, I'll look at exercise 26, and you can practice with 25 and 27. But this is just converting between these different measurements for pressure. There's 26. So 26 is saying, hey, I've got 235 millimeters of mercury. As a pressure measurement. And it's asking me to convert that to these other ones. Let me get it set up. Millimeters of mercury. All right. And it's telling me, give me this in torr, PSI. It wants it in torr, PSI, inches of mercury, and atmospheres. Torr is millimeters of mercury. Let me do PSI first. To convert this to PSI, you take what's over there for millimeters of mercury and put it down here. And we're converting to what? We'll do PSI first. 14.7 PSI is 760. Yeah, that's right. So that's how you would convert it. $235 times 14.7 divided by 760. 4.55 pounds per square inch. What else I got? This one that says convert to torr. Millimeters of mercury is torr. So 760. That's just going to stay the same. They've given it to me in millimeters of mercury, so there's really no conversion. This equals 1. We just end up with this back, so that's kind of silly. What else do I have? Inches of mercury, so I want millimeters of mercury on the bottom, inches of mercury on top. The millimeters of mercury is 760. Inches of mercury is 29.92. So 235 times 29.92 divided by 760. I get 9.25 inches of mercury. And what's the last one? Convert to atmospheres. 760 millimeters of mercury to 1.00 atmospheres. 235 divided by 760. So that's how you use table 1 to convert among these different pressures. 2, 3, 4, 5, 6 different ways to represent pressure. You would think we could drop some of these. All right, so here are some examples for that. You can just practice converting. I skip 10.4 and go take it straight to 10.5. And now for examples, see this PowerPoint that I'm going to upload. This is the ideal gas law. EV equals nRT. Any of you who took chemistry before remember that? Anybody? Yes. E is pressure. V is volume. N is number of moles. R is a constant. And then T is temperature. But be careful, this needs to always be in Kelvin. This is usually in atmospheres, pressure. Volume is pretty much always in liters. Moles is moles. And the constant is liters, atmosphere, mole, Kelvin, usually. Okay. First, let's do this first. So looking at my gas laws PowerPoint, slide number 2, pressure of a gas is 2.30 atmospheres in a 1.80 liter container. Calculate the final pressure of the gas if the volume is decreased to 1.20. Here's what you do when you have these types of problems. R is never changing. Let me get that out of the way for a bit. So what you need to do is identify these. Here's a tip though. If it's not mentioned in the problem, then it isn't changing. Some problems, like in parentheses, will say temperature stays constant. But if it doesn't mention it at all, then it's not changing. So what's changing here? Pressure is changing. What else? Volume is changing. So what is the initial pressure here? And the final pressure, is that what we're being asked for?
Yeah.
All right, volume, what's the initial volume? And the final volume? If you can identify these things, the rest is pretty simple. Moles isn't mentioned, so assume it stays constant. Temperature isn't mentioned, so assume it stays constant. And then you do this. What I'm going to do is, I did this morning too. Let me come back to that. Okay, do this one. All right. It makes more sense if I don't do that one first. PPN. Okay, so do the next one, slide number 3. What will the final volume be? As soon as I read that much, I can do this. What will the final volume be? It will be 3.5 liters. Sample of nitrogen at 20 degrees C, it's heated to 200 degrees C. I did mention the temperature has to be in Kelvin. You see that energy conversion up there. I don't think I put temperature conversions on the test yet, but we went over it ages ago. But you just add 273.15 to any degree C, and that gives you Kelvin. So we've got an initial Kelvin of 293.2. 2 Kelvin. And what's the final temperature? In Kelvin? 473.2. Nothing else is mentioned. Sometimes you'll see in parentheses, pressure stays constant or something. But if it's not mentioned or it's explicitly told, you're told explicitly that it's constant. Pressure stays constant, and the N stays constant. Okay, this is what I wanted to show you. The things that are changing, I want on the left side. The things that are not changing, I want on the right side. And R never changes. So, algebraically, I need to get the P over here. So if I divide both sides by P, I get V equals RT over P. So I've got V on this side. I also want temperature on this side. So I divide both sides by temperature. And I essentially have V over T equals NR over P. There. Now I have the things that are changing on the left side, and the things that are not changing on the right side. Once you get there, you just take what's on the left side here, put ones with it, duplicate it, put twos on it, and now you have a little equation. You've got 1, 2, 3 out of 4 variables you can solve for. This is why I skipped chapter 10.4, is to sneak carefully up to PV equals nRT, and then it's not this easy to work. So to solve this, what I do, I need V2 by itself, so I'm going to multiply both sides by T2. That gives me V1 times T2 over T1 equals V2. And this is what I'm going to use to solve. Follow that? I'll do another one.
Yes. So for you to do the next one, you can switch that to the reference.
Remind me after I get the info on the board to put it back to it.
Table 10.1 and that's PowerPoint.
Yeah, I'm going to put it in PowerPoint.
Okay.
Yeah, they'll have that for the test.
Okay.
Okay. Remind me to go back to the camera. Maybe I should do one of these. Okay, so I can get back to the camera. Let's identify what we got here. The volume of gas is decreased from 2.40 liters from 2.40 liters. To 0.830 liters. So this is slide number 4. Final temperature is set at 40 degrees C, and you see my conversion there. It's 313.2. That's final temperature. Assuming constant pressure, calculate the initial, but I didn't have to say that. It's not mentioned. You just assume. So this is the info we've got. Moles was not mentioned. It's constant. Pressure was constant. So we're not going to deal with those two. It's just volume and temperature again. Let me do the algebra again. So once you identify these things, and you know what you're looking for, not that, it's this that we're looking for, initial temperature. Start with PV equals nRT. Okay, we need volume and temperature on the left side and everything else on the right side. You with me?
How would you know that you don't need to volume temperature?
The information in the problem. Pressure was mentioned, but it was mentioned by way of saying that it's constant. So we know nothing's changing here. Moles wasn't even mentioned, so we assume it's constant. So we're left with volume and temperature. So it's volume and temperature that I want on the left side. So I'm going to use algebra to get volume and temperature on the left and everything else on the right. Divide both sides by T. You get PV over T equals nR. Now I need to get rid of pressure because it stays constant. I want pressure on this side. Divide both sides by pressure. And that gets rid of pressure, and I'm left with nR over P. You follow that? So I've got everything that's changing on the left side. You guys with me? And things that don't change are on the right side. So now I take what's on the left side and I just duplicate it with 1s and 2s. And again, I've got 3 out of 4 of those variables, and I just solved for the fourth one using that equation.
So, with R, do we pretty much always know it because it changes depending on which pressure you're going to use?
Yeah, there is that, but we're not too good. The way I'm doing this is R just ends up getting pushed out of our way. We don't use it. The second part of this PowerPoint has those types of problems. I think I'm just going to stick with atmospheres, liters, moles, Kelvin, rather than the other R values. It really doesn't add anything new to our discussion by changing that up. But you'll see that. You'll see that in the later part.
So you're going to say that your algorithm is everything that changes to the left, and then you spread it to the both sides, which is not going to work.
And the solution is on this PowerPoint. I'm going to upload this PowerPoint so you have problems to look at. But the rest of this is, there's me filling in the details. R is always constant. Here's the algebra. And to solve for, we're solving for T1 this time. So if I took this V1 over T1 equals V2 over T2. I need to solve for T1 this time. So if I multiply both sides by T1, it cancels on this side, and I have V1 equals V2, T2, T1. That's not a smart way to do it. Yeah. What I want to do is, algebraically, to get T1 by itself, I'll divide both sides by V1. And if I clean that up, this cancels, and I have 1 over T1 equals V2 over T2 V1. But now I'm just going to flip both sides to get T1 the way I want it. So if I just flip both sides, I get T1 equals, and now I can just plug in the variables that I have. I've got V1 and V2, V1 and V2, T2 in Kelvin, that'll solve for T1. And I put the answer on the slide here. 906 Kelvin. If you wanted that back in degrees C, you would just subtract 273.15. This one. So far, we've just been doing these where two things change. You can have all four of those things change. V1, V2, M1, M2, T1, T2. All right, look at here on slide number 6. See if you can identify what's going on here. The gas sample is stored in a 429 milliliter container. 429 milliliters. It's at 9.5 degrees C. And you see that my temperature conversion takes that to 282.7. So for temperature, at 9.5 and 2.2 atmospheres. So 2.2 atmospheres is P1. 282.7 is T1. Kelvin, what was the pressure? Pressure is 2.2 atmospheres. Calculate the pressure of the gas if the volume changes to 134 milliliters. And the container is heated to 134.5 degrees, which converted to Kelvin is 407.7. Okay, so we only have this that stays constant. So we need pressure, volume, and temperature on the left. Those are the three things that are changing, so we want those on the left. Divide both sides by T, and you get PV over T equals NR. And now you're going to go P1 V1 over T1 equals P2 V2 over T2. There's 6 variables there. We have 5 out of 6, and we're just solving for the last one.
So for N, do we want to use that value whenever it has a problem?
Yeah. You can also be given grams, and you convert to moles, but we'll get to some like that. Okay, so we're solving for P2. We're solving for P2. So P1, V1, multiply both sides by T2, and divide both sides by V2. I might have walked past you with the algebra, but if you divide both sides by V2, you'll get V2 down here, and it'll go away. You multiply both sides by T2, you get T2 on top, and this goes away. And that's what you would use to solve for this. Just plug and check. There it is. The milliliters cancel, the Kelvin cancel, and you end up in atmospheres, and that's what we want. Guys, okay? So when I start gas laws, I start right there with PV equals nRT. I don't guess I really have questions from 10.3, but let me show you what they are. Should I get these right? Order what I wanted. So Boyle's law, volume and pressure. Volume and pressure. Constant temperature. PV should tell us I just forget which is which, so I have to look. Volume temperature. Moles of volume, I think is So you might come across a problem where volume is changing and pressure is changing. But this stays constant and this stays constant. In which case, you don't have to manipulate this, you're already there. P and V is on the left side. So you'll have P1, V1 equals P2, V2. That is Boyle's law, relating pressure to volume. On the other hand, if its volume and temperature is changing, and everything else stays constant, volume and temperature, you'll end up with volume and temperature in R over P. So you have V1, T1 equals V2, T2. It's Charles' law. It's a statement of Charles' law. And Avogadro's law, now we have changing moles and changing volume. And this stays constant. This stays constant. In which case you're going to go divide both sides by N, divide both sides by P. And V1, N1, V2, N2. That's a statement of Avogadro's law. Which is why I like to do it my way first, because we've already used these. If you just follow my process, whether these people's names pop up in your head or not, you'll still solve it correctly.
the fact that this is Boyle's law and this is Charles' law and this is Avogadro's law, that's just, I don't ever ask anybody, is this Charles' law or is this Boyle's law? It's just, the superior way to do all of it is PV equals NRT. And who cares what it's called? There's more ways we could do this. What if all of these were changed? Then we would have, the only thing I'm on over there now is R, because everything's changing. So I'd have PV over NT equals R, and then P1 V1 equals N1 T1, P2 V2 equals N2 T2. But you know what? There's not a name for that one. So, I mean, why do we name these? There are other combinations too. P to V, there's P to N. There's not a law stated for that one, but you could do that just as well. P to T, V to N, N to T. All of these could have laws. Like I'm listing these pairs that I could come up with. Any of these could have laws. You could also have PV over T is another law. You could have PV over N is another law, but there's not names for those. So to me, they all just derive from PV equals NRT, and the naming of them to me is silly. I mean, I'm happy for them to get credit for their work back in the 1800s or whatever, but I don't know. Naming these laws when we know this governs all of it is just to me extra stuff in a textbook. It doesn't really teach you anything. I should mention the ideal gas. Gases that are very small and don't interact with each other very much is when we use PV equals NRT. There are ways to deal with gases that have strong attractive forces or they're huge molecules, but we won't go through that. You'll take a thermodynamics course one day and learn how to do that, right? Sure you will. So what do I want to do next? Okay, I'm going to go back here. So all of these in this PowerPoint, the header is changing from one state to another. This is when we have the ones and the twos. When you get down here, when you're not changing from one state to another, and I say that just to say, you read a problem and there's not a volume 1 or a volume 2 or a temperature 1 or a temperature 2. You need this. I'll write it up here. Now we need the R constant. 0.086. There's different R constants for different pressure values and stuff, but I'm just going to stick with this one. This is in liter, atmosphere, mole, Kelvin, and those will be the units I use here. And there's no longer ones and twos. R, P, V, N, T. PV equals NRT. Okay, what do I have in this one? Sample of hydrogen gas is added into a 5.80 liter 5.80 liters. It's at 56.0 degrees C. This is slide 10. Converted, the 56 becomes 329.2. Kelvin. How many moles of the gas are present in the container? The pressure is 6.70 atmospheres. Okay, PV equals NRT, 5 variables. You've got 4 out of 5 and you just solve for the thing. You just plug everything in. 7.60 atmospheres. Pressure times volume, which is 5.80 liters, equals N. R is 0.08206
millimeters, atmosphere, Kelvin. And T is 329. And now you're just solving for N. Really what I should have done first is PV equals nRT, and I go, okay, I'm solving for N. This is really what I want to use to solve. Saves a bunch of writing, but I've already written this stuff right there. liters. That'll solve for this. So basically, you have to read the problem to decide whether you have state 1 and state 2, or whether you're just plugging and chugging with PV equals nRT.
What was the answer to that?
1.44 moles. So I will upload this PowerPoint, and if you can keep yourself from looking down at the solution, you can practice these. I'll give you So maybe you want that interface so you don't cheat. You just copy and paste it. Few more of these. This twist is just involving one thing that y'all already know. 2.65 grams of CO2, we're assuming that's an ideal gas. You're given, let's do this. Uh, 2.65 grams. I'm going to write that right here. Because ultimately, I need to turn that into moles. And that's the only twist here. 2.90 liters. Temperature is 308.2. Converted, let's see if I can go on. 2.90 liter vessel. Liters. Pressure. Oh, I have moles. It's asking for calculate the pressure. It's asking for this. And we are going to use PV equals nRT. But CO2 is, there's 1 carbon times 12.01. Oxygen, there's 2 of them times 16. 2, 12.01. So 44.01 grams per mole. So I can find the moles by using the grams. See what I'm doing? That's the only twist here, is you have to go through that step to find the moles. And to find the moles, 2.65 grams of CO2. Grams on bottom, grams of CO2. 1 mole CO2, this should look familiar, equals, you recognize that, right? 2.65 divided by 44.01. So that tells me we have 3 significant figures, 2, 1, 3, 5, blah, blah, blah. So it's that I'm keeping. And now we can plug and check. Now we can solve for solving for pressure. Quickest thing to do is divide both sides by V. And now you can just plug all those values in. And P will come out in atmospheres because of that. Sorry, got to save camera. That makes sense. Question? One other thing I wanted to do today, we were so far ahead. We have 2 more labs to do, so that's going to eat up a couple of days. The only other thing I have to do today, stoichiometry with gases. Exercise. I do expect to get quizzes up of everything. I give you these exercises just so you have something to practice if you want to do it right after class. Do this example. Using R. Atmospheres. Yes. Okay. They give us Kelvin. They want us to solve for liters. This is example 10.14. Given us grams, we can turn into moles. Look at this problem. carbon, that's a solid, plus H2O, that's gas.
So we're doing this at a higher temperature.
CO and H2O. Do this reaction in 22.5 grams of carbon. Grams of carbon is in here. How many liters of hydrogen gas? We're asked for the liters of that hydrogen gas. And it's 1 atmosphere at 355 K. So that's the info we've got. Is this balanced? C and O and H2. It is balanced. We're going to use I'll give you more formula about it. 22.5 grams of carbon. Carbon is 12.01 grams to 1 mole. Carbon. Molar ratio here is 1 to 1. One of these to one of these. 1 mole of carbon to 1 mole of H2. Mole of H2. 22.5 divided by 12.01. 1.87 moles. It's asking us how many liters that'll take up, but it's giving us everything we need. Pressure equals 1 atmosphere. Volume is what we're looking for. Moles we just solved for, 1.87 moles. And temperature is 355 K. And we're in atmosphere, moles, Kelvin. We're calculating liters, so we'll use this R value. Here. I'm going to do the algebra ahead of time. We're solving for V, so we want V equals N R T over P, and then we can plug everything in. N is 1.87 moles. R is 0.08206 liters. Atmosphere, mole Kelvin. Temperature is 355. And pressure is 1 atmosphere. That'll give us the volume in liters. All of that. I guess I'll calculate it and check my answer. 1.87 times 0.08206 times 355 divided by 1. So I'm getting 54.5 liters. I just solved one of the even ones, so I can look that up. 89, chapter 10. 54.6? Close enough. 206, 355, 187. I think they didn't round up what they were supposed to. Or I didn't. 54.5 is what I got. One point 87 times 0.08206 times 355. I get 54.5. That was 89. Equation we got is 2H2O that's my reaction. My picture came up. Info here is that's the reaction. What mass of HO? Extra info is temperature equals 315 K. Pressure is 0.981. This time we're going for the mass of H2O. So we're kind of doing this backwards. We're going to use PV equals nRT first to find moles, and then we're going to use moles to solve the rest. So we've got temperature, pressure, and volume. So I'm going to find moles that way. I've got temperature, I've got pressure, I've got the liters, and temperature, pressure, liters, and I'm going to find moles. Yeah, I'm solving for moles, and then I'm going to go on from there. All right. Pressure, atmospheres, volume, 1.85 liters. R is 0.08206 liters, atmospheres, mole K, and then what, temperature. That'll tell me how many moles. This is a gas. That matters here. 0.06 divided by 315. The moles I get here is 0.0702099.5 blah 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 3343. So I'm keeping the 702. So basically I've got 0.0. All right. The rest of this should look familiar. Moles of O2, we have 1 mole of O2 to 2 moles of H2O. So it asks us for mass, so H, there's 2 of them, O, there's 1 of them, times 1.01 equals 2.02, times 16 equals 16, 18.02 grams per mole for water. I want moles on the bottom. 1 mole of H2O is 18.02 grams of H2O. That'll tell us what mass of water we get. 1.85 liters of oxygen. Follow that? What do I get? 0.0702 times 2 times 18.01. 18.02. I got 2.53. Grams H2O. 2.53 grams of H2O. Guys follow that? Let's see what other variations. We're going to convert the mercury, the millimeters of mercury, to atmospheres. And then we could so ask for volume. All right, first, let's take, this is 92. 92. And our equation is aluminum, 3, 2 gas, 2, okay, what's our information? Volume of O2, liters. It says 25 degrees C, says 782 millimeters of mercury. Volume is what we're looking for, so we need to find moles some way. I'm going to convert the 782 millimeters of mercury first. first. Atmospheres. Atmospheres is 1.00 millimeters of mercury. Its torr, which is 760. 782 divided by 760. We've got 1.03 atmospheres. And I'm going to convert 25 degrees C to Kelvin. 273.15 plus 25, 298.15. If I do this correctly, eliminating that, so 298. All right, so that's done. Okay, so we're going to find volume of O2 with 53.2 grams. Of aluminum here. Okay, so we'll do this. Grams per mole for aluminum. Aluminum is 26.98. 26.98. 1 mole. Now we use our mole ratio, AL to O2. Moles of AL go at the bottom. So 4 moles of AL to 3 moles. That's what we want, moles of O2. 53.2 times 3 divided by 26.98 divided by 4, and I get 1.48 moles of O2. The rest is PV equals nRT. You with me? So I'll use that. So I divide both sides by P to get this. I'm solving for this. All right, what do we got? Moles is 1.48 moles. R is 0.08206 meters in atmosphere. Kelvin. I'll just put temperature over here. 298K divided by pressure, which is 1.03 atmospheres. 298 times 1.48 times 0.08206 divided by 1.03. So if you do that reaction, putting in 53.2 grams of aluminum, the amount of oxygen that burns would take up this many liters of oxygen. You guys okay? All right. If there's any other variations?
more of these? Huh? You think you have enough that you can practice them? This is us. Covered on the 12th. This one I'm kind of skipped. I'm not sure what else is going on test 3. There's at least 1 or 2 more sessions we should have. But, so if you look at the calendar, I won't see you Friday. Monday or Wednesday we'll do the lab. I'm thinking I'd rather do it Wednesday. So I'd lecture more there. So I basically have 2 more lecture periods, maybe 3. No, 2 more lecture periods, test 3, review for the final. Yeah, so we really only have a couple more lecture periods that we'll cover. So be practicing this stuff.